County summaries and United States agricultural reports from the 1880s routinely estimated rodent damage in stored grain at 5 to 10% a year, higher where grain sat in small wood-bin storage. On the northern plains, that figure was not an abstraction. A 2-ton holding in a pole granary could lose 200 pounds or more to rats and mice over a single winter. Ledgers from country stores recorded the consequences in ink. Discounted sacks marked chewed, extra flour bought on credit by March, seed short in April. Most pole granaries stood on 4 rough-sawn posts, about 3 to 4 feet high, built to a widely accepted pattern. In railroad towns and larger mills, a different pattern appeared: smooth sheet metal rat guards wrapped around posts and pilings. Where those were installed correctly, inspectors recorded almost no loss from climbing rats. The arithmetic would decide which design stayed on the open plains and which quietly disappeared. Summer 1884. Homestead Belt west of Huron, Dakota Territory. Fresh 6x6 posts set in post holes, damp earth still clinging to the auger. New plank floor framed about 42 inches above the sod. Huron sat on the Chicago and Northwestern line, a rail point that drew wheat farms within 10 to 20 miles of the tracks. Grain moved by wagon from field to either town elevator or on-farm storage. Where farms held their own crop through winter, waiting for better prices or saving seed and feed, the standard solution was a raised pole granary. Farm manuals and agricultural bulletins of the period recommended a simple pattern. An 8 by 12-foot floor of 1 1/4 inch plank rested on 4 corner posts, 6 by 6 or 8 by 8 timbers sunk 2 feet into the ground and extending 3 to 4 feet above grade. Single board walls, often board and batten construction, enclosed the space. A simple gable roof with shingles or rough boards kept out rain and snow. Interior capacity ran around 4,000 pounds of wheat or oats stored in sacks or loose in cribbed bays. The design answered several challenges efficiently. Raising the floor above grade kept the grain away from ground moisture and snow accumulation. The structure required minimal lumber and could be framed by 1 or 2 men in a few days. Posts were readily available from nearby timber along creeks or hauled in by rail. The whole assembly cost perhaps $15 to $25 in materials, a modest investment for a season's crop storage. Agricultural literature of the 1880s explicitly endorsed this approach. One widely circulated farm manual advised that grain houses should be raised from the ground upon posts or underpinning to prevent moisture and to discourage the depredations of vermin. The assumption embedded in that sentence that height alone would discourage rats reflected common understanding across the wheat belt. Builders optimized for speed and economy. Posts were rough-sawn, not planned. Corners used simple notching or lap joints. Floors were tight enough to prevent grain from spilling through, but gaps of 1/4 inch or more between planks were not unusual. Walls closed the space but were not sealed like house construction. The whole structure prioritized function over finish. What the manuals did not address in detail was exactly how rats would respond to the barrier of height. The literature mentioned cats, traps, and poison as active defenses. It assumed that a raised floor combined with these measures would keep losses to an acceptable minimum. That assumption would be tested by every winter's ledger. The design raised the grain 4 feet into the air, but every rat that reached the floor still found only soft pine and loosely stacked sacks. Winter 1885 through 1886. Same region, county courthouse, and general stores across central Dakota Territory. Ink-faded ledger page on a counter with one column headed Grain, another tagged Loss, Damage, numbers cramped in the margin. Agricultural bulletins and county reports from this period documented rodent loss in farm storage at 5 to 10% of stored volume, with some sources citing higher figures where storage was in open cribs or small bins not made rat-proof. The range was not theoretical. On a typical 2-ton granary holding, 5% meant 200 pounds lost. 10% meant 400 pounds, the equivalent of nearly 4 full sacks of milled flour or enough seed wheat to plant several acres. Store ledgers recorded the practical consequences. Incoming sacks from farm storage were marked down as must be ground at once if gnaw damage was visible, rat-chewed if holes penetrated multiple layers of jute, or short weight if the contents had been significantly depleted. Farmers settling accounts after threshing found their delivered grain discounted or rejected outright if damage was severe. Local reports and farmers' correspondence from the period note seed shortages in spring, particularly after hard winters when families had drawn more heavily on stored reserves. Letters mention running short of flour by late winter and buying additional supplies on credit. These shortages were not catastrophic in most years, but they represented a steady erosion of the margin between self-sufficiency and debt. The accepted pattern treated this loss as normal overhead. Most farmers assumed that some portion of stored grain would be lost to rodents, just as some portion of a harvest might be lost to weather or handling. The question was not whether rats would get into the bins, but how much they would take. 5 to 10% seemed tolerable, especially when weighed against the cost and effort of more elaborate construction. Alternate patterns existed. Elevator operators and millers in larger towns favored tight bins with hardware-clad foundations and sealed joints. Inspectors visiting these facilities noted lower damage where floors and supports were smooth and inaccessible. But these were commercial operations with access to materials, skilled labor, and inspection protocols. The standards applied there did not routinely transfer to small farm structures. Weather notes from this winter show moderate cold, not yet the severe season of 1886 through 1887. Temperatures ranged from near zero to the low 20s Fahrenheit with intermittent snow. Grain losses occurred under what the records called average or ordinary conditions. The design was failing not during crisis, but during normal operation. In ordinary winters, before any severe test, the accepted design wrote off every 20th pound of grain. The ledgers proved the loss. The posts remained unchanged. Autumn 1886. Northern Plains and older settled regions of New England and the Great Lakes. Time shift explicitly marked. Weathered granary on stone or mushroom staddlestones in an older farm region, frost beating on the smooth stone caps under the wooden sills. Storage patterns varied across regions and building traditions. In parts of the northern forests and plains, indigenous groups used raised caches on poles with overhanging platforms, designed to limit access by climbing animals. Food and seed stores were elevated on supports that incorporated a horizontal barrier, a wide platform or projecting log section that broke the direct vertical climb path. In New England and parts of the Great Lakes region, older granaries and corn houses often rested on staddlestones, shaped stone piers with a narrow base widening to a broad, smooth cap. The wooden structure sat on these caps. A rat or other climbing animal reaching the top of the narrow stem encountered a smooth, overhanging surface with no purchase points to continue upward. The geometry of the stone itself created the barrier. These systems used physical principles rather than height alone. An overhang interrupted the climb path. A smooth, hard surface reduced friction and eliminated claw-hold points. Where such systems were properly maintained, caps kept clear of debris, supports not bridged by stacked materials, rodent damage was noted as a nuisance rather than a structural failure. Ethnographic notes and farm building descriptions from various regions mention food stores secured against rats by raised overhanging supports. A report from the Great Lakes region described corn cribs on stone piers where rats cannot ascend owing to the shape of the supporting stones. Another account from New England noted granaries raised upon mushroom stones which prevent vermin from reaching the floor. The principle was understood in these older building traditions. A vertical path could be broken by changing the geometry or surface character of the support. Stone provided mass, durability, and a naturally smooth surface when properly dressed. Carved wood could create similar overhangs, though it was more vulnerable to rot and required more maintenance. On many Western homesteads, the new bins copied the footprint of older granaries, but omitted the crucial feature. The posts were simple vertical timbers, rough-sawn and untreated. They provided support and elevation, but no interruption in the climb path. The knowledge that had been embedded in stone shapes and carved platforms did not transfer when builders switched to faster, cheaper methods using raw posts. Metal could replicate the function of stone or carved wood without the mass or masonry skill. The question was whether that knowledge would reach the wheat belt before another generation of bins wrote off another decade of grain. November 1886. Farmyard edge at dusk, same Dakota belt. Frost crust along the lower 2 feet of a damp 6x6 post. Claw marks faintly visible in the rime where the surface is rough. Rough-sawn posts carried visible texture. Saw blades left longitudinal ridges. Grain tear out during cutting created shallow valleys and raised splinters, often 1 to 2 millimeters deep. To a human hand, the surface felt relatively smooth. To a rat's claws, each irregularity was a potential purchase point. A large brown rat weighed approximately 3/10 to 1/2 kilogram. During vertical ascent, the animal distributed its body weight across multiple claws, front and rear, engaging small irregularities in the wood surface. The combination of claw sharpness, distributed contact points, and body posture allowed the rat to maintain sufficient friction against the post to climb steadily. Planed lumber presented a different surface. The planing process removed saw marks and grain tear out, leaving a smoother face with fewer irregularities. Painted surfaces filled remaining texture and created a harder, more uniform skin. Metal, particularly sheet iron or galvanized steel, offered a surface even smoother than planed wood, with minimal texture and high hardness that resisted claw penetration. Early technical texts on rat control, published in the early 1900s but drawing on observations from prior decades, noted that rats ascend nearly any rough surface, including brick walls, wooden posts, and rough-cast plaster. The same texts recommended smooth metal bands or collars to prevent climbing onto ships' mooring lines, pier pilings, and storage structures. The principle was established in maritime and warehouse settings well before it reached agricultural bulletins. The physics were straightforward. Increasing post height from 3 feet to 4 feet only lengthened the climb. It changed nothing about the interface between claw and wood. A rat capable of climbing 3 feet could climb 4 or 5 or 6. The limit was not the animal's strength or endurance, but the availability of surface texture to grip. On granary posts across the wheat belt, the evidence was visible after every damp night. Frost outlined claw marks in dense bands, concentrated between knee and chest height, where the climb was steepest and the rat's weight pressed hardest against the post. The marks showed consistent paths, the same routes used repeatedly as animals climbed to the floor, fed, and descended. The same physics that allowed a rat to climb a granary post also allowed it to climb a pier piling. Yet only one of those structures routinely received a smooth barrier. The difference was not in the problem, but in which industries had formalized a solution. December 1886. Multiple homesteads across one township. Composite view of reported practice. A post darkened with axle grease to mid-thigh height. Dust and chaff already stuck in a gritty layer. A shallow pan of water half frozen at the base. Farm families shared advice through local papers, grange meetings, and direct observation. Agricultural columns in regional weeklies printed readers' suggestions for controlling rats. The remedies most commonly mentioned fell into three categories: greasing posts, setting posts in water pans, and nailing deterrents to the wood. Greasing posts with fat, lard, or axle grease initially reduced friction. On first application, the surface felt slick, and a rat attempting to climb would lose purchase. But the effect degraded rapidly. Dust from threshing, chaff from feed handling, and fine dirt blown across the yard adhered to the grease within days. The sticky layer collected debris, creating a new textured surface, gritty, irregular, and in some ways easier to grip than bare wood. Reapplication restored the effect temporarily, but maintaining a slick surface required frequent attention, especially during active farming seasons. Water pans presented a different challenge. The idea was to create a moat, a barrier of liquid that rats would not cross. Shallow metal pans or wooden troughs placed around each post were filled with water and checked periodically. In moderate weather, the method had some deterrent effect. But in northern winters, standing water froze solid within hours of the first hard freeze. Once frozen, the surface became a bridge rather than a barrier. Snow and wind-blown debris accumulated in the pans, raising the effective floor and giving rats a new platform to begin their climb. Nails, spikes, or random tin shards driven into posts at intervals were intended to create an impassable barrier of sharp points. In practice, the spacing between projections often provided intermediate footholds. A rat climbing between spikes simply adjusted its path, using the projections themselves as additional grip points. The method also posed risks to livestock brushing against the posts and to people working near the bins. Farm Journal notes from the period acknowledged these limitations. One column remarked that such measures were troublesome to keep up and soon lose their effect. Another noted that greasing and watering posts required constant attention to maintain any deterrent value. No published report from this era showed a measurable drop in total loss percentages attributed to these improvised methods. The more effort farmers spent greasing, watering, and spiking posts, the more the records showed grain losses staying within the same 5 to 10% band. The remedies consumed labor and materials while leaving the fundamental climb path unchanged. March 1887. Depot and Warehouse District at Yankton, Dakota Territory. Place and context shift explicitly marked. Telegraph pole by the freight platform, a galvanized sheet metal disc bolted around it about 3 feet off the ground. Rain and coal smoke streak the smooth surface. In towns and along rail corridors, posts and pilings supporting stored goods or infrastructure routinely carried metal guards. Telegraph and utility poles used sheet metal collars to discourage animals from climbing and damaging lines. Warehouse supports and wharf pilings, where bulk flour, sugar, and grain were stored, incorporated similar barriers to block rats from reaching upper levels. The devices were simple in concept. Thin sheet iron or galvanized steel, typically 18 to 28 gauge, was formed into flat collars or shallow cones. Diameter ranged from 18 to 24 inches, wide enough to create a significant overhang beyond the post's profile. The metal was fastened tightly around the post using bolts, nailed flanges, or crimped edges that left no gaps large enough for a rat to squeeze through. Some designs flared downward, forming a shallow cone that shed rain and made the underside even more difficult to grip. Sanitary engineering texts from the late 1800s described metal rat guards on ship mooring lines and pier pilings as standard practice. A manual on warehouse construction recommended smooth metal collars or bands fitted around all supporting posts to prevent rats from ascending to stored goods. Another guide, focused on port facilities, specified that guards should be of sufficient diameter and properly secured to eliminate all pathways for climbing vermin. Where these guards were installed and maintained, kept clear of bridging debris and checked for gaps. Inspectors reported greatly reduced rat access to upper structures. The method was proven, documented, and already in widespread use in settings where rodent control had economic or public health importance. Yet the transfer of this knowledge from depot and warehouse to farmstead was incomplete. Farmers building granaries in the 1880s generally did not include metal collars in their designs. The pattern they followed came from agricultural manuals that emphasized raised floors and active control measures, cats, traps, poison, but rarely mentioned structural barriers on the posts themselves. The disconnect was not a matter of technology. Sheet metal was available through hardware, suppliers, and could be ordered by rail. Tin salvaged from worn-out roofing or stovepipe could be repurposed. The barrier was not material availability, but information transfer. The method that kept dockside sugar bags safe was proven long before most plains granaries were built. It simply had not crossed back from wharf and depot to the section lines where wheat was stored in family-scale bins. 1895 through 1915. Agricultural experiment stations in the upper Midwest. Time jump explicitly marked forward. Bulletin page laid on a station workbench showing a simple line drawing. A wooden post with a flared circle of metal midway up. Agricultural experiment stations, established under federal and state programs in the late 1800s, took on the task of formalizing and testing farming practices. Extension agents investigated problems reported by farmers and conducted trials to evaluate solutions. Rat damage in stored grain was a recurring topic in station correspondence and field reports. By the mid-1890s, several stations had begun systematic trials comparing grain loss in bins with different construction features. Bins with tight floors and sealed walls showed lower losses than those with loose joinery. Bins with posts protected by smooth barriers showed markedly lower losses than those with bare, rough posts. These results were compiled into farmers' bulletins, short publications distributed free or at minimal cost through mail, county agents, and agricultural societies. Bulletin language was direct. One widely circulated publication on rat-proof farm buildings stated, "To prevent rats from climbing posts that support granaries or other storage structures, fit a smooth metal collar to each post, of sufficient width and securely attached, so that no gap remains through which a rat may pass." The bulletin specified collar dimensions, typically 18 to 24 inches in diameter, and recommended mounting height at 2 to 3 feet above ground to avoid splashing mud and typical snow depth. Diagrams accompanied the text. Simple line drawings showed posts with circular or conical collars, often with small detail sketches illustrating how to cut and fasten the metal. The drawings were not to scale and contained no complex dimensions, making them reproducible by farmers with basic tools and materials. Station reports noted marked reduction or practically eliminated rat damage in bins where collars and tight floors were used together. One summary stated, "Where properly maintained, such guards are nearly completely effective against climbing rodents and should be considered essential rather than optional in farm storage design." The information was now formalized, reproducible, and backed by field data. What had been scattered industrial practice was now written guidance available to anyone who requested a bulletin. Adoption on small farms depended on access to materials. Time 2. Implement the design and awareness that the bulletins existed. On paper, the stations had reduced rat damage in test bins to nearly zero with a few square feet of sheet metal. Yet many field reports from farms that had not seen the bulletins still logged the same 5 to 10% losses. The method existed. The question was how widely it would spread. Practical pattern, circa 1900. Generic small grain farm on the northern plains. Synthesis of prior decades. Length of salvaged galvanized roofing laid across sawbucks. Compass-scribed circles faintly visible in the zinc coating. Translating bulletin diagrams into a working retrofit required basic tools and modest material. A farmer or hired hand with carpentry experience could complete the work in a half-day for a standard 4-post granary. The process followed a clear sequence. First step, measure the post. Using a flexible tape or string, determine the circumference at the height where the collar would be installed, typically 2.5 to 3 feet above ground. Add 2 to 3 inches of overlap allowance to ensure a tight fit when the metal was wrapped and fastened. Second step, lay out the circles. On a flat sheet of salvaged roofing tin, galvanized steel, or even heavy stovepipe sections, scribe 2 concentric circles using dividers or a makeshift compass. The outer circle should measure 18 to 24 inches in diameter, wide enough to create a substantial overhang. The inner circle should match the post circumference plus overlap. The area between these circles would form the collar. Third step, cut radial slits. From the inner circle outward toward the outer edge, cut radial slits at intervals around the circumference. These slits allowed the metal to be bent and shaped. The resulting tabs could be bent upward 90 degrees to grip the post. Fourth step, form the collar. Wrap the cut sheet around the post at the desired height. Bend the inner tabs upward tightly against the post surface. The outer portion should form a shallow cone or flat skirt, angled slightly downward to shed water and create an overhang. Fifth step, fasten securely. Use closely spaced nails or small bolts to secure the tabs to the post. Eliminate gaps. Any opening larger than ½ an inch could allow a rat to squeeze through. Check the entire perimeter, adjusting and adding fasteners as needed. Material cost was minimal. Salvaged roofing carried no direct cost beyond the labor of removing it from an old structure. New sheet metal cost a few cents per square foot at period prices, often less than the market value of a single 120-pound sack of wheat. 4 collars for a typical bin required perhaps 2 to 3 square feet of material per post, a total investment of less than $1 in materials. Time investment, approximately 30 to 45 minutes per collar, accounting for layout, cutting, fitting, and fastening. A full retrofit, 4 posts, could be completed in 3 to 4 hours of focused work. Labor saved, reduced nightly trap setting and cleanup, less time sorting damaged grain, fewer replacement sacks bought on credit. A morning's work with tin snips and scrap metal could protect more grain than an entire winter's work with traps, if the geometry was right and the airspace stayed clear. Winter 1901 through 1902. Documented grain farm in the Dakotas or Upper Midwest, as reported in extension summaries. Interior of a raised granary by lamplight, seams of a few sacks showing frayed, chewed jute along the lower edges. This winter served as a baseline in records compiled by agricultural extension agents documenting rat control measures. The farm operated a typical 4-post pole granary with a capacity of roughly 4,000 pounds of wheat and oats, enough to hold a season's supply for seed, livestock feed, and household milling. Recorded losses in this winter, drawn from station reports summarizing typical conditions, ranged from 5 to 8% of stored volume due to rats and mice. On a 4,000-pound holding, that equaled 200 to 320 pounds. The equivalent of 2 to 3 full sacks lost to gnawing, spillage, and contamination. Evidence of access was clear. Gnaw marks appeared at floor level near the posts, where rats emerged after climbing the rough supports. Droppings accumulated along sill plates and in corners where grain was piled. Several sacks showed frayed seams where rats had chewed through the jute to reach the grain inside. Other sacks were marked short weight when weighed out, their contents partially depleted over the course of the winter. Weather tables from this season showed it was not extreme by Northern Plains standards. Temperatures ranged mostly from -10 to +20 degrees Fahrenheit. Snow accumulation was moderate, rarely exceeding 1 foot on level ground. This was an ordinary winter, neither mild enough to reduce rat activity nor severe enough to drive exceptional damage. The farm operated with standard control measures. A barn cat hunted mice around the granary and adjacent structures. Spring jaw traps were set nightly along baseboards and near the granary door. Poison bait, mixed cautiously to avoid harming livestock or children, was placed in covered stations near known rat pathways. These measures reduced visible rat populations but did not eliminate access to the stored grain. Rats continued to climb the rough posts, reach the floor, and feed on the sacks. The losses recorded in this winter were typical, not catastrophic, but steady and predictable. Under these conditions, the baseline was clear. Ordinary construction, with rough posts and active control measures, could not prevent a significant margin of loss. Even in a relatively mild season, the structure and its unprotected supports guaranteed that a portion of the stored grain would be surrendered to climbing rats. Station notes from this period admitted that ordinary construction could not be expected to hold its grain without considerable depredation by rodents. The numbers confirmed it. 5 to 8% loss was the accepted norm. Accepted not because it was tolerable, but because no alternative pattern had yet reached widespread use. Winter 1902 through 1903. Same farm, same bin, after retrofit described in bulletins. Snow banked to within a foot of the posts. Thin ring of metal visible midway up each post. Frost beaded on the underside of each collar. The retrofit occurred in late summer of 1902, following guidance from an agricultural extension bulletin obtained through the county agent. 4 sheet metal collars were fabricated from salvaged galvanized roofing, cut to approximately 20 inches in diameter, and installed at approximately 30 inches above ground level on each of the granary's corner posts. Installation followed the bulletin pattern. Each collar was wrapped tightly around its post, with no gaps left between the metal edge and the wood surface. The inner tabs were bent upward and nailed securely. The outer portion formed a shallow cone, angled slightly downward. The surrounding area was kept clear of brush, stored lumber, or other items that could act as ramps bypassing the guards. Grain stored in this winter was of similar quantity and type to the previous year. Weather conditions were comparable, temperatures in the same range, snow accumulation moderate. The farm continued using the same cat and trap program as before. The only significant change was the installation of the 4 metal collars. Inspections through the winter, documented in extension follow-up reports, noted no new gnaw marks on sacks stored above the floor level. Droppings at ground level indicated rat presence around the granary's perimeter, but the rats were not reaching the floor. The climb path had been interrupted. Spring wayout showed negligible loss. Total grain removed from storage matched the quantity put in, minus only small amounts attributable to spillage during handling and minor mouse activity at the door threshold, losses that had always existed and were not related to climbing rats. The 5 to 8% loss recorded the previous winter had effectively disappeared. Extension reports summarizing these and similar cases noted marked reduction or practically eliminated rat damage where collars and tight floors were used together. One bulletin stated, "Bins equipped with properly fitted metal guards show rat damage reduced to trace amounts, limited to spillage and incidental access points unrelated to post climbing." The contrast was stark. Same structure, same location, same general weather, same baseline rat population in the surrounding area. The only variable was the interface at the posts, bare wood versus smooth metal with overhang. The loss numbers tracked that, changed directly. In one season, the ledger column that had reliably recorded 200 to 300 pounds lost now recorded only minor spillage and handling waste. The grain was still there because the rats could no longer reach it. The method worked exactly as the diagrams said it would, provided the installation was correct and the area stayed clear. 1900 through 1915. Various farms and station test sites across the Midwest. Time and place broadened to show variation, Snowdrift packed tight against a bin, completely burying one collar. A plank leaned against another side as a makeshift ramp. Not every installation succeeded. Extension agents revisiting farms that had adopted the collar design documented cases where the method failed to reduce losses. The failures followed consistent patterns, all related to installation errors or maintenance lapses. The most common failure mode was burial. Collars mounted too low, within 18 to 24 inches of ground level, were vulnerable to snow accumulation in heavy winters. A drift piling 2 feet high against the granary completely covered a collar installed at 2 feet. Rats simply walked across the top of the compacted snow and continued climbing the post above the buried guard. In these cases, the collar existed but was not functioning. The barrier had been bypassed by natural accumulation. The second failure mode was bridging. Farms that used the area around the granary for temporary storage often leaned materials against the bin. Fence rails, extra planks, bundles of straw, or bags of feed. These items, if they reached above collar height, created ramps that rats could use to bypass the guards entirely. One report noted a granary where firewood had been stacked against the north wall, reaching within a few inches of the floor. Rats climbed the woodpile, jumped the small gap, and accessed the grain despite the presence of correctly installed collars on all 4 posts. The third failure mode was poor workmanship. Collars installed with gaps at the inner edge, where the metal did not fit tightly against the post, allowed rats to squeeze through if the opening exceeded half an inch. Loose fastening, where nails or bolts were spaced too far apart, allowed the metal to flex and create temporary gaps. One station report described a collar that had been installed with only 4 fastening points, leaving sections of the circumference unsecured. Rats found and exploited these gaps. Bulletin revisions incorporated these lessons. Later editions specified minimum mounting heights to exceed typical snow depth for the region, emphasized the need to keep the area around supports clear of all materials that might provide climbing access, and stressed that gaps must be eliminated by close fastening and proper fit. The same device that cut losses to a trace on one well-maintained farm made almost no difference on another where snow was allowed to pile, or debris was stacked carelessly. The underlying idea was sound. The results depended entirely on whether the design conditions, clear space below and around the collars, tight fit with no gaps, were respected. 1915 through 1935. North American farmsteads and early poultry operations. Time jump marked forward explicitly. Small poultry house on posts, each support wrapped with a metal cone, chickens moving in the yard below. The homestead era passed, but the principle remained. As wheat farming became more mechanized and commercial grain storage shifted to larger, professionally managed elevators, the small pole granary gradually disappeared from the plains landscape. But the method of using smooth metal collars to prevent climbing animals from accessing elevated structures found new applications. Poultry keeping, which expanded significantly in the early 20th century, faced similar problems. Chickens housed in elevated coops were vulnerable to predators that could climb wooden supports, rats seeking eggs, raccoons seeking chicks, and snakes seeking both. Poultry manuals from this era routinely specified metal guards on coop posts, using nearly identical geometry to the granary collars. One widely circulated guide on farm poultry production, published in the 1920s, included a diagram labeled Predator Guard for Elevated Coops. The illustration showed a conical sheet metal collar installed midway up each post, with text advising, "Fit a smooth metal cone around each support post to prevent rats, weasels, and climbing snakes from reaching the floor. Cone should be 18-24 inches across and mounted high enough to avoid burial in snow or debris." The same principle appeared in wildlife conservation plans by mid-century. Nest boxes for wood ducks, Bluebirds and other cavity-nesting species were mounted on posts to protect them from ground predators. Conservation agencies specified smooth metal cones, often called predator guards or baffle cones, around the posts to prevent raccoons, snakes, and rats from climbing to the nest entrance. Modern nest box plans still include these guards as standard equipment. The relationship between surface texture, overhang geometry, and animal access, once understood, was applied wherever the same problem appeared. The materials varied. Galvanized steel replaced salvaged tin, preformed cones replaced hand-cut circles, but the underlying function remained unchanged. A smooth, overhanging barrier interrupts the climb path. By the time most pole granaries had rotted into the soil, the same few inches of metal were still performing the same function. The structures changed. The species changed. The principle did not. Elevation alone was never sufficient. The interface between climber and support determined access. Change that interface, make it smooth, make it overhang, and the climb fails. Long after most pole granaries had collapsed, the same thin sheet of metal was still doing the same job under chicken houses, duck boxes, and feed sheds. Mid-20th century. Interpretive farm or museum site. Raised granary preserved with metal-wrapped posts. Museum label beneath a small, weathered granary, noting vermin guard collars around each post. The metal dull and pitted, still intact. The numerical impact was clear when calculated over time. On a 2-ton grain holding, cutting losses from 5 to 10% down to near zero saved 100 to 200 pounds per year. Over a decade, that margin equaled several full wagon loads of grain, seed for multiple acres, flour for months of household use, or cash income from sales delayed until prices improved. In frontier survival arithmetic, those margins mattered. Families operating on narrow cash reserves could not easily absorb a 200-pound shortfall every winter. Grain lost to rats meant grain bought on credit at the country store, debt carried into the next season, or seed borrowed from neighbors with the obligation to repay at harvest. For farms that installed collars correctly and maintained them, that pressure disappeared. The grain they stored in autumn was the grain they withdrew in spring. Preserved farm records and interpretive texts at historical sites allow modern visitors to connect these unobtrusive collars to measurable changes in household economy. One exhibit label notes, metal rat guards, though simple in design, often determined whether a family held their own grain supply through winter or bought flour on credit. The difference was not dramatic in any single season, but compounded over years into the margin between staying and leaving. The principle was straightforward. Identify the path of loss, interrupt it with appropriate materials, and verify the result with numbers rather than assumptions. The method did not eliminate all grain loss. Spillage, handling waste, and mice at ground level remained. But it removed the largest single category of structural loss: rats climbing rough posts to reach the stored sacks. What began as an industrial and sanitary engineering detail, metal guards on warehouse pilings and telegraph poles, became a quiet but decisive factor in small farm resilience once the knowledge reached the homesteads that needed it. The transfer was slow and incomplete. Many farms never saw the bulletins. Others saw them but lacked access to materials or time to retrofit existing bins. But where the method was applied, the ledgers recorded the result. On preserved posts at interpretive sites, the thin collars look minor, almost decorative. Visitors often pass them without noticing. But the arithmetic in the old ledgers makes their status clear. A few inches of smooth metal properly placed and maintained often mark the line between grain lost to vermin and every sack accounted for. If you value fact-grounded frontier history and practical build methods like this, consider subscribing or supporting the channel so we can keep documenting how small decisions in timber, metal, and layout changed who stayed through winter and who left.